we're going to take a look at the regioselectivity of the Hofmann elimination using this example. And what we have in this molecule is, there's our alpha carbon where the amine's attached, but we have two different beta carbons with beta hydrogen that can undergo the elimination. I want you to recall something you learned in Organic 1 about elimination reactions. And that is predicting the product for the Zaitsev product and the Hofmann product. So the Zaitsev product is the one where you get the most substituted carbon-carbon double bond possible. The Hofmann product is where you get the least substituted carbon-carbon double bond possible. And this term falls out of this Hofmann elimination reaction. And what we find is that when you have regioselectivity to choose from, we're going to end up with the less substituted double bond. Let's start by doing our first two steps and drawing what we get so we're set up to do the elimination. So after you methylate the nitrogen, we get this, and then from the ion swap you have hydroxide around as well. So then when we go to heat this up, we have our two different beta hydrogen to choose from. I've drawn in the two different types of beta hydrogen, and if we eliminate from beta hydrogen A, the base attacks that proton, and we get the double bond. Now here I've drawn the cis double bond, but you could also think about the trans double bond. But now if we go to HB and do the same thing, use our base and attack it, and do the elimination, we get this product. Now if you look at the double bond substitution, in our first product, it's a di-substituted alkene. In our second product, it's a mono-substituted alkene. So because this is a Hofmann elimination, the mono-substituted is going to be our major product. That's the product of the reaction, and that's why I really didn't care about the cis or trans in this first product anyway. So why is this? So here I've redrawn the molecule, and if we draw in the hydrogen at both beta carbons, do that and that. What you have to realize is this trimethyl ammonium group is a really large group and it takes up a lot of space. So that bulkiness is hindering the molecule as it is. And then if we look at the hydrogens, and my picture may not be the best representation, but if you build a molecular model, it would be easier to see that at this less substituted carbon, the hydrogen are more accessible. So you already have this bulky group blocking these two hydrogen, and then you have this methyl group kind of blocking them, so it's more difficult for the hydroxide to come in to this more substituted carbon. It's easier to come in to this less substituted carbon where you just have three small hydrogen.